Hopefully everything's getting recorded fine. Hoping everything is getting recorded fine, to be honest, and it's recording to the cloud properly. I'm having a couple of troubles with this new Zoom system that they did at Chafee. It doesn't give me as much information as you saw. One of the items, either for this class or for the other class at Chafee, ended up recorded onto my computer as opposed to the cloud. Made it a little bit hard to get it, circulated. But hopefully I've got that all worked out now. Okay. Go ahead and share screen. So we're going to start by looking at our monkey problem. Okay, so this was our wildlife biologist, if you recall, right? Everybody see my screen here?
Yeah.
I'm just trying to get up my chat window and my who's online here. So we're going to work through a couple of these. So this one here showed this picture. Okay, so we need to come up with separate equations. And the correct answer is you point at the monkey. So let me see if I can manage to draw this picture a little bit less with not quite as nice of cartoons. But I've got a point here where my dart is. And well, let me start over already. I have a point with the dart here. I have my monkey over here. My monkey is, I'm just looking by eye. My monkey is X0 monkey and Y0 monkey. Okay. And in our case, so I'm just going to have X0 monkey, Y0 monkey. And in our case, we were given 10 meters and 10 meters. It's 10 meters above and 10 meters below. Now, in order for it to hit the monkey at all time later t, the vector position at D and at some time t, the vector position R and the vector position for the monkey, vector position for the dart and the vector position for the monkey have to be the same at some time t. So let's write down what those conditions are. So I have to, at the time final, TF, we can write R dart at T final has to equal R monkey at T final. Or X dart at T final has to equal to X monkey at T final. And Y dart at T final has to equal to Y monkey at T final. So this is just reiterating the conditions. Those are just the conditions. So I don't know theta 0 and I don't know T final. So I don't know those problems. Now I could try to play with range and height equations, but they're just difficult. We need XD final and YD final at T final. So XD of T final is equal to X0 dart plus V0 X dart times T final plus 1/2 A sub X dart T final squared. This, of course, is free fall, so this is 0. There's no acceleration in the X direction. And X0 dart was 0. And this has to equal to x monkey t final, but there's no motion in x, so that's just x0 monkey. That's just x0 monkey. So x start t final is equal to v0x of dart t final, which is equal to x0 monkey. So it's just its speed times the time has to equal this distance. Everyone agree with that so far? Can I get agreement there?
Yes.
Okay. Y dart t final is equal to y0 dart, which is also equal to 0, plus v0 y dart times t final. And we'll just go straight to what our equations, minus 1/2 g t final squared. That has to equal to y monkey at t final, which is going to equal to y0 monkey minus 1/2 g t squared. So here we have a 0. Let's write out this part and this part on another line. So we have v0 y dart t final minus 1/2 g t final squared is equal to y0 monkey minus 1/2 gt squared. But gt squared and gt squared are both on the same side, so we can just cancel these two out together. So v0y dart over t final times t final equals y0 monkey. And v0y of v0x of dart times t final as equal to x0 monkey. So now look at this. So now I can go to here and I can go, well, if these are equal, then v0y dart over v0x dart has to equal to y0 monkey over x0 monkey. Those ratios are constant, no matter where the monkey is. Okay, no matter where the monkey is, these ratios stay constant, the v0y and v0x. And look at this angle here. Theta, the tangent of theta is equal to v0y dart minus v0x dart over v0x dart. That's definition of tangent theta, but that's the same as if we look at this of y0 over x0 for the monkey. So that's equal to y0 monkey over x0 monkey. So no matter what the condition, I always point at the monkey. No matter about the 10 meters, 20 meters, 30 meters, this could have been, the monkey could have been here, the monkey could have been the same distance way over here. You know, it doesn't matter. You always point at the monkey if the monkey is going to let go as soon as you blow the dart. If the monkey doesn't let go as soon as you blow the dart, all those bets are off. But the fact is we have this minus 1/2 gt squared, but he starts at the ratio of the height to length is that they're equal. So it works out, we get the minus 1/2 gt squared on both sides. And we have the same equation for the x distance in terms of the monkey's distance and velocity and the y distance in terms of the y position of the monkey. So we're always pointing at the monkey. So you follow this through down into this line here.
Yes.
Okay. So for the first half of this path, we're coming up, but the second half it's going down. And that is equivalent to starting up here and just falling. Okay, let's look at the next question I said I would do. Okay, I had this archer aims at a target. And I showed you a batch of different ways to look at it. One of the reasons I show a batch of different ways is so you look at different ways to think about it and define for yourself what is the best way to look at it. So an archer aims at a target. Now, we're going to start at, there's our target over here. And so this is position 0 and 1.5 meters. This is position 55 meters and 5 meters. Okay. And over in this position here, when it hits at this position, so this is x0, x of some t, and this is y of some t. And my v, I have v0x, no, I have v sub x, not v0x, v sub x, t, and 0. Okay, because we're given 0 y velocity. Now, first thing I'm going to do with this problem is I'm going to subtract 1.5 from each. And I'm going to remove my origin. I'm going to move my origin to here. So this is this is ground down here. And I was saying this was 0, 0. Remember, I told you you're free to choose the origin. So I'm going to move my origin up to here and up, and then this is 3.5, and this is 0, 0. So I'm just going to redraw this picture here. I'm going to call it 0, 0, and 55 meters and 3.5 meters. Okay. And I only do that because it makes my kinematic equations of motion easier. Okay. So let's look at my conditions that we have here. We still have v sub x of t and some velocity there and 0. So let's look at my equations here. I can write out one equation that's common to use is x equals x0 plus v0 xt. And I really don't have all the information I want for that one right now. I can write y is equal to y, which is just equal to v0x times t. This is 0. Equal to y0 plus v0y times t minus 1/2 gt squared, which is just equal to v0y times t minus 1/2 gt squared. But again, I don't know time. But I can also write v squared is equal to v0y squared, v sub y squared, minus 2g y final minus y initial, or y0, y minus y0. So that leads to, and v sub y squared is equal to 0. So that leads to 0 at the condition right here, because v sub y0 was 0. V sub y wasn't, v sub y0 isn't 0, but right here, we're told it hits horizontally. So my v sub y of t is equal to 0. So I have 0 is equal to v0y squared minus 2g times 3.5 meters. Or I can write v0y is equal to square root of 2 times 9.8 meters per second squared times 3.5 meters. And we get to some extra significant figures, 8.283 meters per second.
We're unable to see your all of your screen.
Are you seeing it here?
Just the part of it.
Okay, well, you're gonna lose the very top of it because I can make it smaller, but I can't make it the whole screen and a reasonable size.
No, that's good. We got it now.
Okay, so I have to slide up. Okay, so I've got what v0y is. Now, I can also go and say, remember that a sub y, by definition, is equal to delta v sub y over delta t, or this leads to, which is the same as minus g equals delta v sub y over delta t, or delta t is equal to delta v sub y over minus g. T is t final minus t initial, and t initial is 0, so we're just going to write that as t. T final minus t initial equals just t, because this is going to be 0. We're just going to write delta t as t for the purposes of in this equation, because we started at t time equal to 0. We're just going to write it as t. Delta v sub y is equal to 0 minus 8.283 meters per second. V final, V initial, over minus 9.8 meters per second squared. And so this is equal to, I don't know where I got to 65 here accidentally. Okay, so 0.283 and 9.8 divide, and that's equal to 0.845 seconds. Okay, so look here, we have v0y. We better make sure we put a circle around that so we know where we have it. Now, x is equal to v0x times t, and we have t. So v0x is equal to x over t, which is equal to 55 meters over 0.845 seconds, which is equal to, and with that, multiplied by 55, 65.07 seconds. And so v, our speed, not the vector, is equal to the square root of v0x squared plus v0y squared, which is equal to, so I'll square this, 8.283 squared. Add those two together and take the square root, and I get 65.59 or approximately, now I'll do my two significant figures, 66 meters per second. Okay, but I've got one device and I was given enough of the information. Remember when I said things about implied, you have to look about the implied variables. One of the problems that students often have with this sort of problem is it says the arrow is completely horizontal after sticking to the target, i.e. the arrow was traveling horizontally just before hitting the target, right at the instant of hitting the target. That implies its y velocity is 0. If it's traveling horizontally, its y velocity is 0. And I wrote that down explicitly up here. But I go and I do my drawings. And I first did the drawing just as they wrote it. Now, if I was writing this, and just solving this problem, and I just got in, my job was to just solve the problem, I would have just started right here, 0, 0, 55, 3.5. And I wouldn't have written the 1.5 and the 5 up front, because it was irrelevant. Now it's relevant. That 1.5 is relevant versus the 5. If I asked you, how far distance would it be when it hits the ground? Because then it needs to hit the ground at 0 meters in y. So it'll go 110 meters, twice this distance, before it's back at 1.5 meters, and then it's going to go some distance further before it hits the ground. It still can be relevant in certain aspects of the problem, but this aspect of the problem, it wasn't relevant. So I just moved my equations up to here because I wanted to get the speed of the arrow, and that was all I was going to worry about. Had I not done that, then I would have put x as 5, or x as, I still would have had x 0, but now my y would have been 5 and 1.5, which still then would have had the same 3.5 when I moved it over here. So when I moved it down over here to get V0y, okay, and then when I got AY, so here I had, if I did y final minus y initial, I would have had 5 minus 1.5, still would have been 3.5. Instead, I did 3.5 minus 0. It still comes out. It still works out just fine. And you can do it as you most like it. And delta y still would have been 3.5. Okay, but it's just convenient for me because I like to cross off as many variables as quickly as I can. Okay, so you see how those two problems are solved? Any question on those two problems? Trying to find a second here. Having a lot of problems with seem to be having a lot of problems with the Zoom system today. Okay, so let's go on to today's lab. Okay, did everyone open up today's lab yet?
Yes.
Okay, so on today's lab, we are doing projectile motion. Did I upload the correct one? Oh, yeah, I think so. Yeah, good. So we're just having a little bit, most of this lab is just, there are two pieces of this lab. One is you can do it by brute force running the lab. Okay, I am sharing my screen, correct? Good. Okay. And that is the method you're going to go through is basically, you're going to try different values and find out what happens. Okay. Again, we're using this GeoGebra format of simulation today. But what we want to do is we want to take a reasonable guess at a initial condition. Sometimes one uses simulations or stuff in the lab to find solutions to complex problems. For example, suppose I have ax squared plus bx plus c equals 0. Now you all know how to find x for this, right? X equals negative b plus or minus square root of b squared minus 4ac all over 2a. Pretty convenient, right? Quadratic formula. Everyone agree that that's pretty convenient? Now, what if I had ax cubed plus bx squared plus cx plus d equal to 0? What would you do? Well, it turns out there's another formula to solve for x that gives you 3 roots for x, and there's another formula that does solve for x. Okay? And if I have ax to the 4th plus bx cubed plus cx squared plus dx plus e equals 0, there's yet a formula that solves that, a closed form solution. But it turns out, and it's been proved mathematically, that if you have ax to the 5th plus bx to the 4th plus cx cubed plus dx squared plus ex plus f equal to 0. There is no closed form solution for that. There is no actual closed form solution. What I mean by a closed form solution is this is a closed form solution. I can write down a solution that involves my coefficients, and then I can get my different roots of this quadratic equation. This I can write down an equation that gives me the roots of my cubic equation. I can write down an equation that gives me the roots of my equation to the 4th power. There is no equation that will give the roots to 5th power or greater. Now, how is one of the ways that you solve those? You guess and you check. But you don't want to just guess arbitrarily, randomly choosing values of x. You guess and you check. So if I guess a number for x, I go in and I fill it in, and then I check and see if that works. Well, we're going to play a little guessing and checking on this simulation. Now, it turns out I have a simulation that the problem does have a closed form solution. And all of you have enough math to solve this closed form solution. It is nothing beyond algebra to solve the closed form solution. And if you find the way to the closed form solution, that's great. Just show that it's correct at the end. But if you don't want to find the closed form solution, which is, by the way, faster to do that with a closed form solution, if you know right off the bat how to do it, or you might, challenge yourself to find it even after you solve it through a bit of guess and check. But guess and check doesn't get done without trying to zero in on the answer. And that's what we're going to do in this simulation. So what have I set up in this simulation? We're going to use this projectile. And you're going to have to be a little bit careful in here. Okay. And it just has projectile motion. Now, what is projectile motion? Projectile motion, of course, has our formulas that y And we're always going to start at 0, 0. So it's just going to equal to V0YT minus 1/2 GT squared. We're always going to start at Y0 equals 0. Leave that one at 0. So you don't have to put in a value for Y0. Okay. And we're going to look at, and you don't have to put in a value. There's also a place, I think there's a place to put in a Y0. There may be a place to put in one. Hang on one second. So I can put in Y0. So I can move it up, and I can only leave X0 as 0. But X, we're just going to leave it at 0, 2, and it's V0X times T. So don't adjust your Y0. Don't go making this, moving it higher. Okay? At least that's my recommendation. If you want to make it higher, you're going to want to make it something like, you could in principle go and make it 150 meters higher, but I don't know if you can even set it that high. It has a limit that you can only go to 100. So we're going to keep it at 0. And you're just going to have to look at the answers on the problem. Okay. Now, let's consider this figure here. We have a cannon over here, and it's sitting on the ground. And it launches with some speed, V0, some velocity, V0, in some vector angle. So it's got theta 0 and speed V0, which I've written as V0 vector. And it needs to go up. It needs to pass through a window that is 500 meters in the horizontal away from the cannon and 200 meters up. So that means it needs, at 500 meters away, my projectile needs to be between 199 meters and 201 meters to pass through this window. Everybody understand that?
Yep.
Okay. And I want you to hit a target down here. I want you to hit a target down here, 750 meters in the horizontal away, but it's actually going to be below where the cannon was by minus 150 meters. So you're shooting from behind a cliff through some sort of fortress wall down into some pit, if you will. And it's minus 150 meters below the cannon and 750 meters away. So you got to be, so you can look at this right now and say, well, the apex of this needs to be somewhere around 300 meters. I need to be coming down through I'm going to have some sort of arc like this because I'm well past the apex. If I was going through the window on the way up, it would be hitting way over here. So I can't be going through the window on the way up. I have to be going through the window on the way down, and I need to figure out what that is. Now, what I want you to be doing here is I want you to do some guess and check. Now, as I say, it turns out there is a closed form solution. Now, what have I written here? I've written that you can do this two different ways. You can choose on the simulations to put in a velocity and an angle, or you can separately put in the horizontal velocity and the vertical velocity. You can put them in separate. I like using the horizontal velocity and vertical velocity because that I can make more sense with. Okay. Now I'm going to hit print on this. I want a copy of this page. Give me 1 second. It should only take a second to print. if I don't have any errors in my printer, which is a rarity in and of itself. As it's printing. Okay, give me 1 second to grab it. It'll make it easier for me to. Hang on 1 second here. Okay, I didn't realize I didn't have my video going. You can tell me that in the future. I'll try not, even on a bad hair day, I will film myself. Give me 1 second here. So your goal here is to meet those conditions. Okay? The projectile is going to start from 0, 0. Okay, when the projectile is at 500 plus or minus 1 meter, the Y position must be at 200 plus or minus 1 meter. When the projectile is at the Y position, not the X position, minus 150 meters, the X position must be 750 meters plus or minus 1 meter. So X1, Y1 is 500, 200, X2, Y2 is 750 minus 150. Okay, and we're going to go into and try to do this. Now, first thing you do, you're not going to have to write down every attempt. You should write down a fair number of attempts. Now, note down here, I have launch velocity and angle, or initial horizontal velocity and initial vertical velocity. You can write down either one. I want you to make sure you write down the time at target, at the window, and time at the target impact. Give me a spot to write each time down. I'm not so worried that you fill in time for each one of your intermediate ones, only when you get to your final one that you say is the correct answer. And you need to have more than one filled out because I won't believe it otherwise. So if I go to this, I'm going to start, and I'm just going to, I need to set up an angle. I'm going to start with a 45-degree angle and a, I don't know, I'll start with a velocity, I don't know, about 70 meters per second, just for that. You're going to need to choose something. And I'm going to hit fire. And I'm going to zoom out. And I'm going to pause it. Now, if you look over here, I can move my time. Look, I haven't even hit X equal to 452 meters. And I'm way low. So I'm certainly not at 200 meters at 500. So I'm not even going to bother with recording that one because I know that I'm way low. So I'm going to increase my launch angle. I'm increasing it a lot. Okay, look there. Okay, at least I'm above 200 meters here, but I'm nowhere near 500 meters in X. So I'm going to increase my velocity. Okay, that got some of each, but it made this one big. Now I'm going to reduce my launch angle again. Okay, and you see, I'm starting to get in the ballpark here. I got 522.94 meters. I got 202.44 meters in Y. I'm starting to get in the velocity. So I'm going to switch to initial horizontal and vertical velocities. Okay, and I'm going to start with, I don't know, I'm going to move this down to like a whole number just because I don't want to write out a whole lot of numbers. I'm going to make this 57 because I don't have anything better to choose. And I'm going to make this, say, 66 even. Nope, 66 wasn't enough, but let's go back a little bit. Oops, I didn't want to do that. Zoom in. Okay, now I can do this time slider. It's a little bit difficult to work with. You can do that to get it like in the area, but then if you move these up and down arrows, they move it in 0.01 seconds. So right here at 500 meters, I'm at 201.75. I hope I don't get too close too quickly. I'm not trying to. So I'm going to make this say 65.9. Oh, I did something wrong there. 65.9. 65.8. Okay, so I got 199.99 and 500.46. Okay, so there I've hit 1 point. So I go to my paper here and I go initial horizontal velocity 57, and I know everything's in meters per second. And y is 65.8. X1 was 500.46. And the height at the wall was 199.99. So that's all really close for that position. And if you want, you can write in this T 8.78. Now I'm going to move to X equals 750 meters. And I have it 745.46 here. So now I'm going to use these little arrows because it's really hard to move this too far, but I wanted to go quickly, go over close. There's 750.12. I have 750.12. And the Y position is 17.32. And my T is 13.16. Okay, now it's clearly not low enough. Now, when I change my Y velocity, it has two effects. My Y velocity will change both will change my time of flight, so it'll change my X position, okay? But it won't change the X position at the same time. So it change my time of flight before it hits the ground. Okay, but I'll start to come lower to the ground. So I might sit here and go, oh, how do I get this to work? Well, you might try different things. I might try, for example, well, when does Y hit minus 750? Minus 150. So there, that's there. Okay. And now I'm going to reduce my X velocity to hit 70. So I already wrote down what these conditions were, but I need to make another guess for my next set of conditions. Now, I might decide to look at X1 and Y1 first, but I can decide to look at X2 and Y2 first. So I've decided to set, so my Y is about minus 150. Now I'm going to go reduce my X. I can use the slider or I can type it in. Notice when I change X, my Y doesn't change. So I'm going to go to say 48.5. So now I'm going to go look here. Well, I reduced this to 48.5. And I left this at 65.8. Now my X2 is 747.87. And my Y is at minus 150.47. And it's 15.42. Now, I'm not going to say that that was necessarily a good choice. But what I've done is I've moved in on my X. So I have X meeting here. And I'm deciding that I'm going to adjust my X over here. And I'm going to adjust my Y velocity over here. Maybe that's a good choice. Maybe it's not. So the first thing I need to do is I need to move back to where X is 500. And I'll use my arrows here to get it close to my 500. So at X, for these same initial velocities, 500.04, and I wouldn't worry about necessarily writing down too many significant digits at first. I'm 157.55. And this was at 10.31. So my next guess is going to be to increase my Y velocity some. So Y now comes to 200. So now my next guess, I'm going to do a horizontal velocity of 48.5. And now 70. Now X1 is 500.04. Y1 is 200.85. Time is still 10.31. Now I got to see where it went to at X2 and Y2. Now I know this seems a little tedious. So I'm going to go to where Y2 is, Y is now minus 150 again. So here Y2 is minus 150.18 and X is 784.73. And it's 16.18. Okay, now hopefully at this point you see what I'm doing. I'm changing one at a time. So here I had, this was my first guess. Now this wasn't actually my first guess. This was my first guess that was in the ballpark. I just played with it till I got something in the ballpark. You know, even close to start guessing at. Here, I left the vertical the same and reduced the horizontal to, okay, so on this one, I set my first condition, so I met 500 and 200. That's pretty easy to find, and that's like one to write down. But my target isn't met. At 750, I was still 17 meters above the launch position, not 150 below. So I adjusted my Y position, my Y velocity, or I adjusted my, and then adjusted my horizontal velocity so that when, and my Y, and put my time, I changed my time here. So I set up Y2 at minus 150 and adjusted my horizontal velocity to meet the 750. And then I went back and I checked X1 and Y1 was now too low. So I increased my vertical velocity to get this back in line, because I went from 65.8 to 70, while holding my horizontal velocity constant. And now, to be at minus 150, I'm 784. So now I go ahead and adjust my x velocity again, because if I adjust my x velocity, it affects only this number. So I adjust my x velocity to say 750. $46. Let's call it 46.2. 46.4. That's pretty close. So now I go 46.4 while leaving the 70 constant. My x2 is 750.75. My y2 is minus 150.18. And this is 16.18 still. And when you move back so that x is 500, it's 500.19. And I'm at 185.18. Now you see how here I hit everything good, but I was way off. Here I brought these in reasonably close, but I'm off. So I increased my vertical velocity to bring these back in, and these are off. So then I bring these back in, and this is off, but I'm getting closer and closer. So now I'm going to adjust my y and bring this back in, and this will be off. I'll adjust my x to bring both of these in, and this will be off. And I keep walking in and zeroing in. And that's how you do intelligent guess and checking. And that is really done. You know, sometimes we can do it, you can set up simulations to do that, but that's how a lot of simulations work. So we're doing a lot of the mechanics behind simulations. I call these simulations. These are more computer animations. We're not taking values that have some unknowns and solving for unknowns. We're putting in knowns and then seeing what the values come out. So these are almost more of animations and just purely simulation. But you know, we're using it to simulate and find these answers. If I was using an equation, this is a full-on simulation, I would build in, okay, this condition isn't being met, change this. This condition isn't being met, change this. And I build that into a loop in a simulation. And that's what's really done when you do simulations. There are thermal simulations to find the steady state. What does a small change do? How does it affect it? And what's the steady state? So you're going to fill out the rest of this. And that's really all there is to this lab, because when you go out on the rest of it after that, okay, when you get the final results, you're going to give the initial velocity, horizontal velocity, and vertical velocity. If you did it that way, you're going to give it at the time 1 when it passes through the window, and the time 2 is the target. The horizontal position T1, the horizontal position at T2, the vertical position at T1, and the vertical position at T2. You're going to write down what the values are that you recorded to say 5 significant figures. That's what your simulation gives you. And using the kinematic equation for motion, for projectile motion, confirm the values obtained in the simulation. Now let's be really clear what that means. Okay, what do I mean by that? Part 2. You wrote down T1 and T2. You have V0x and V0y and V0y. Okay? X of T1 is equal to V0x T1. X of T2 equals V0x T2. Those are the times that I've been writing down here. You know, the time, here's my X position, the Y position, the X position, Y position, the time. Now, you're going to get it down. You're going to keep going through here until you find you meet these conditions of 500 and 200 plus or minus 1, 750 and minus 150 plus or minus 1. You're going to find the times that meet that condition. You're going to write those down in here where the condition is met. This is the initial velocity. These are your positions. So basically what you're going to do is you're going to be, hopefully it's your last line on here that meets these conditions. You're going to write down all your values here. You're going to write down what those times are here. You're going to go in here. This is the equation for X of T, because X0 is 0. Y of T1, Y0 is 0, is equal to V0Y T1 minus 1/2 G T1 squared. Y of T2 equal to V0Y T2 minus 1/2 G T2 squared. Okay? That's using the kinematic equations. You better get answers on these that are in agreement. They don't have to be exactly the same, but they better be in very close agreement with the horizontal position at T1 given by the simulation and the horizontal position at T2 given the simulation, the vertical position at T1 given the simulation, in the vertical position at T2 given in the simulation, and these positions that have to be in agreement with these positions must meet these conditions. The horizontal position at T1 must be 500 plus or minus 1, and Y1 must be 200 plus or minus 1, and Y2 must be minus 150 plus or minus 1, and X2 must be 750 plus or minus 1. You must meet these conditions, and when you get your times here, you need to validate that your simulation work, that your kinematic equations of motion give the same result. That's all your simulation is doing. It's supposed to be running those kinematic equations of motion. If you ran this in Cartesian coordinates, which I expect you will, because I would expect you'll probably more or less just continue on with what we've done here. Convert to velocity. Remember, 3 V0 is just equal to the square root of V0x squared plus V0y squared. And theta is equal to the arctangent of V0y over V0x. Now, at that point, you're going to go into here. I want to say if you answered yes, so at that point, once you go in here, you're going to switch back to set angle and initial velocity. This has initial velocity and launch angle. And you're going to decrease this. So let's say 83.98 was correct. You're going to decrease it by 0.5 meters per second. So you put in 83.48. Then you would determine whether there is a launch angle that can be adjusted to still meet these conditions. Okay, I think I've actually set it tight enough that there isn't, but maybe I didn't. Okay, I set your conditions. So point is, it is, when I have 2 points, it's a unique parabola. Now, if you want to solve the quadratic equation describing a parabola to calculate the angles in advance, you can. You can solve. You have. I've given you 3 points. I'm going to give you a hint how to solve this. I'm going to encourage you to do it both ways because hunt and check has its value to just part of doing physics and part of doing anything in experimentation. You go into biochemistry, you know, there is tediousness of it. There can be, you know, 90% pure boredom followed by 10% of pure terror. Okay, not everything in the lab is exciting. Okay, but when you get your final result, it makes all that tedium to be quite worthwhile. But we have 3 conditions for X and Y that we know we have to meet. We have 0 and 0. We have 500 and 200. And we have 750 and minus 150. The quadratic equation y is equal to ax squared plus bx plus c. Okay, that's it. I'm not writing that equal to 0 because I'm not. Okay, y of x equal to 0 equals 0. Y of x equal to 500 equals 200. And y of x equal to 750 equals minus 150. Okay, that is your equations of that you have. So I have 3 equations. I can put in x equals 0, and these are unique equations. Some will tell you need 5 points on a parabola to really solve it. That's only if you choose a couple of degenerate points. These are non-degenerate points. Okay, x equal to 500 and y equals 200. So 200 equals a times 500 squared plus b times 500 plus c. Okay, and here 0 is equal to a times 0 squared plus b times 0 plus c. You should note right away, c equals 0. Okay, you figure that one out right away. Okay, and then you have minus 150 is equal to a times 750 squared plus b times 750. So you can solve for what a and b are because you have the 2 equations and 2 unknowns. Okay, and this is y equals ax squared plus b. You also have y is equal to y0, which equals 0, plus v0yt minus 1/2 gt squared, which is equal to v0yt minus 1/2 gt squared.
Can you move the page up a bit? Thanks.
I don't know why you don't get my whole page. I think that somehow you're getting from my screen off. I still had almost half my screen to look to see. I'm not quite sure what's going on here. Okay. So I'm happy to move it up though, of course. So I've got y. I've also got x is equal to x0 plus v0x times t, which is just v0x times t. So you can use this. You can stick it in here for x once you figured out your a and b's. Okay, you want to figure out your a and b's just doing it this way. And then you compare what you get after you stuck in here to what this looks like. And you can find that you can quickly pull out what v0x is. And once you have v0x, you can figure out what v0y is, because you have a and b as a relationship as well. So I've given you a lot more hints than I've given classes in the past on this. give you a lot of hints on how to do this with the quadratic formula. Just say you can do it as you like. I encourage you to do it both ways. So I gave you some hints on here. I gave you actually a lot of hints. Past that, you're going to have to figure out the rest of the way to do it. And just look at what you get out as you do it. But do this substitution and compare the terms that are, give you one other hint here, just real quick. So y is equal to a v0 squared plus b times v0 plus c. So I substituted x in here. We're going to follow this out for a, b, and c first. And now you got a term that's got t's, t squares, and c and y0. Well, c, y0, no t, they're both 0, 0, so that works out. You know, b v0x kind of looks like v0y. It's just got a t in there. A v0x squared kind of looks like minus 1/2 g. So you can look at this and say, oh, these coefficients must be the same. The coefficients in front of t here, they got to have the same value because I've got it written and they've got to carry out the same thing. So that's actually a lot of hints to solving this. But hopefully you look at that and you can look at then how that's one of the ways that we go to try to solve equations like this. So that's the end of what we have for today. Any questions?
Not yet.
And my sigh is just because my voice gets being on camera for 3 hours. You just get your voice gets a little worn out. And I try to talk really loud so that everyone can hear me. Because everybody's speaking is different. So I'm not.
Tutoring session, I gotta go. Thank you.
All righty.
Bye.
I'm not mad when I'm talking loud. I just talk loud to try to project myself. Okay, any questions? Any questions on homework? Any questions next week? The lab session is going to be review. A midterm review. I will post a review worksheet within the next couple of days, and we will go through some of those review worksheet problems. If you've been finding some particular homework problems or some particular quiz problems, as challenging, please bring them up to me. I do look through them. I do look at some that I find that people were challenged on and then go ahead and do them. But I need you guys to give me feedback or ask questions. This is all two-way here. All right? Sometimes when I watch the screen, I'm not even sure if anyone is still online. All right, well, I know that one person is still online. I've had situations where people just dial in because they think lab is getting taken and they disappear for an hour and a half. So please bring questions, because I just can't believe you all understand it perfectly and have no questions at all, ever and forever. So anytime you have questions, please bring them. I get lonely just, being the only one talking. All right. Thanks, guys. We're done.